In clinical practice, there is a persistent assumption that what you ingest is precisely what your body uses. You calculate the total dietary intake on a spreadsheet, assuming that dropping a nutrient into the stomach guarantees its delivery to the cells. This graph illustrates the paradox. On the left, a rapidly climbing bar represents a massive oral intake of an isolated phytonutrient. On the right, the corresponding serum biomarker line flatlines. The nutrient enters the body, but it never reaches the blood. Systemic bioavailability is not dictated by the gross volume of food swallowed. It's entirely governed by the microscopic immediate chemical environment inside the gastrointestinal tract. This brings us to nutrient synergy. This is the biochemical phenomenon where co-ingesting specific molecules dictates their chemical behavior. One nutrient can alter another's absorption kinetics, force a receptor to activate, or trigger enzymatic cleavage. To understand how this works, we will examine three distinct mechanisms. First, lipophilic transport, anabolic threshold signaling, and pharmacokinetic antagonism. Ingesting a nutrient is clinically useless if the surrounding biochemical context prevents its systemic delivery. The lumen of the human gut is a highly aqueous, watery environment. This poses an immediate physics problem for certain essential nutrients, bringing us to our first interaction mechanism, lipophilic transport assistance. This diagram shows a 3D cross-section of the intestinal lumen and the enterocyte brush border. Notice the beta-carotene molecules. Because these carotenoids are hydrophobic, they repel the surrounding water, clumping together. They cannot penetrate the aqueous mucosal layer to be absorbed. The clinical catalyst required to break this barrier is the co-ingestion of monounsaturated fatty acids, or MUFAs, typically found in foods like avocados. Dietary lipids trigger the gallbladder to release bile salts. These salts act as emulsifiers, mixing with the MUFAs and encapsulating the clustered beta-carotene. This creates a spherical structure called a mixed micelle, which easily ferries the trapped carotenoids across the watery lumen and directly to the enterocyte cell surface. Once inside the enterocyte, an enzyme called BCO1 attaches to the beta-carotene molecule. It cleaves the molecule exactly at its central double bond, which yields two active molecules of vitamin A. These newly synthesized retinol esters are then packaged with lipids into chylomicrons and released into systemic circulation, where they support retinal health and immune cell priming. This table shows exactly how powerful the synergy is in clinical trials. When raw carrots or tomato sauce are paired with avocado, alpha-carotene absorption increases 4.8 times. Beta-carotene absorption surges by up to 13.6 times. Look at the final column. By adding that single source of fat, the actual conversion of these precursors into active vitamin A jumps by an astounding 15-fold. This chemical dependency happens elsewhere. For example, piperine in black pepper inhibits specific digestive enzymes in the liver and gut, which increases the bioavailability of curcumin by 2,000%. Manipulating the local lipid matrix converts a biologically useless phytonutrient load into a highly bioavailable therapeutic dose. Beyond the mechanics of absorption in the gut, we must examine how nutrients trigger cellular signaling, specifically within skeletal muscle tissue. As humans age, they develop anabolic resistance. Muscle cells become less sensitive to protein signals, accelerating sarcopenia, the severe age-related loss of muscle mass. In these older adults, standard dietary protein intake fails to prevent this physical decline. Muscle protein synthesis does not happen simply because raw amino acids are floating in the bloodstream. Building muscle is metabolically expensive. The tissue requires an obligatory signaling trigger to begin translation. This model illustrates the mTORC1 pathway, the primary receptor responsible for this anabolic switch. A slow, disorganized trickle of generic amino acids impacts the receptor, but the concentration is too low. The pathway remains dormant. To activate this receptor, the cell requires a highly concentrated bolus of one specific essential amino acid, leucine. When enough leucine arrives simultaneously, it locks perfectly into the mTORC1 receptor, flipping the switch from dormant to active. Once activated, mTORC1 phosphorylates specific downstream targets, namely P70S6K and 4EBP1. This rapid cascade of signals travels deeper into the cell, commanding the machinery to initiate the transcription and translation of new proteins. Clinicians call this the leucine threshold. It requires approximately 3 grams of leucine in a single meal to guarantee mTORC1 activation in older adults. Crossing this threshold yields immediate results. The muscle fibers begin rapidly knitting together, thickening and expanding as new myofibrillar tissue is generated and repaired. This is why the standard protein recommendation of 0.8 grams per kilogram of body weight per day is systematically insufficient for aging populations. To consistently hit that 3-gram leucine threshold per meal, the daily intake must be adjusted to a target of 1.2 to 1.5 grams per kilogram. Dietary protein must be prescribed not merely for total raw mass, but to successfully breach the specific biochemical threshold that forces cellular repair. We now turn to the inverse principle, pharmacokinetic antagonism. This occurs when specific food matrices actively disrupt and neutralize targeted clinical interventions. The most immediate antagonistic threat happens in the gut through a process called chelation, where molecules form tight, restrictive bonds with metal ions. This diagram shows a quinolone antibiotic molecule encountering a calcium ion in the gastrointestinal tract, perhaps from dairy or a fortified supplement. The two molecules physically snap together, forming a locked, rigidly bound complex. Because of this chelation, the new antibiotic calcium complex is now too large and structurally clumsy to pass through the intestinal wall. It is rejected by the barrier and remains permanently trapped in the gut lumen. This interaction reduces the absorption of the antibiotic by up to 36%. A third of the medication is rendered useless, directly risking infection treatment failure. Antagonism also occurs beyond the gut, migrating into the liver through systemic enzymatic interference. This model of the liver's cellular environment demonstrates how the blood thinner warfarin operates. Warfarin acts as a vitamin K antagonist. It binds to specific enzymatic sites, successfully blocking the pathways that synthesize clotting factors 2, 7, 9, and 10. But observe what happens when a sudden influx of dietary vitamin K is introduced. A massive wave of molecules floods the environment, overwhelming the warfarin blockade. The enzyme pathways are forced to rapidly reactivate, releasing the clotting factors back into the blood. If a patient inconsistently consumes large amounts of leafy greens, this fluctuating dietary input constantly overrides the prescribed anticoagulant effect, causing dangerous spikes in blood clotting potential. To manage this competitive inhibition, complete elimination of vitamin K is not required. Instead, strict dietary consistency is the necessary clinical strategy to maintain a stable drug response. Failing to account for local chemical antagonists can completely neutralize the efficacy of highly potent pharmacological therapies. Zooming out to a systemic view of the human body, we can see that these interactions happen simultaneously across different organ systems. The gut handles lipid micellization, the skeletal muscle awaits the mTORC1 threshold, and the liver manages enzymatic inhibition.